So let's get into some technical definitions and things. This chapter is all about linear relations, so we're not going to stop at just graphing. We're going to graph very specific things. A linear relation. Does anyone want to take a guess at what might be meant by this term linear and relation?
Like we use that for stars.
Use it for stars?
Don't we?
What do you mean?
Linear, like the linear. I've heard that in space. Yeah, the linear socials English.
Oh, so linear. Okay, so what? So yeah, linear is your socials and English situation.
Round.
So what does, in the context of your education, linear is opposed to semestered, where like your math is semestered. You only have it for half the year. Linear, you have it the entire year. It goes straight through the entirety of your year. Sorry? Yeah, but you have it all year. It's a linear awkward situation that switches all year. That is not. I mean, it's kind of related to what we're talking about here, but not not as related as I would like. Linear has what four-letter word at the beginning? Okay. So a linear relation is and we're not just going to say line because this is technically a line, but this is not linear.
It's a straight line.
It's a straight line. And then relation is relationship.
With another spot? Oh, I see.
Between two variables. So often in science, this is where this really starts to show up. Also in like economics, when you're dealing with money, there is a relationship that exists between two variables. If I tell you that, every CD is $5, and you have, 5 CDs. You guys don't even know what CDs are. Yeah, you do know what CDs? Okay, that brings me a little bit of hope. Back in the day when we bought CDs, there's a direct relationship between the number of objects you purchase and the total cost, depending on the cost of an individual. There's a direct relationship there. It's not like you buy, if 5 is $5, 10 is going to be $10. It's not like 10 is going to cost you $15. Like where it curves up. It probably is not making any sense. That's not making sense. Forget I said anything. We'll bring it back to specific examples here in a sec. So we want a straight line relationship between two variables. Most of these demonstrate a straight line relationship between two variables. The important thing before we get into talking about which ones do which, something to note is that the points in the relationship, we'll say points on the graph, do not need to be connected. Sometimes it makes sense to connect things, sometimes it does not make sense to connect things, depending on the context of the question. So, which of these 6 graphs gives us a relationship a straight line relationship between the two variables? The first one does. This one is y, this one here is x. If x is 1, then y is 1. If x is 2, then y is 2. It goes up by the same amount in both directions each time. So this one is, check. Which other ones are? Second one is, it's a different relationship. For this one, when you go over in x, you're actually going down 2 in y, but that's true every step of the way. Like if I go over 1, I go down 2. If I go over 1, I go down 2. It's linear. What else? The third one?
Yeah.
If I were to connect those dots, would it form a straight line? Yeah. What is a context where we might not want to connect those dots? Where it would not make sense to connect those dots?
When they're not related.
No, they're certainly related here. The variables are related.
When it's not on
Not necessarily. Carolyn, did you have a thought?
maybe like
Yes. If there's no like in-between measures of things. Absolutely. So like here we have this dot right here means we're including this point on here where x is allowed to be equal to 1. But for whatever reason, x is not allowed to be equal to 0 or 2, but x is allowed to be equal to 3. If for whatever reason there are values that we're restricting, it would make sense to not connect these dots. So like the example that Carolyn gave, if we're buying CDs, can you buy half of a CD? No. So it wouldn't make sense. So like on, let's look at this one right here. This is linear. But these lines are not connected. Actually, this isn't a great one. I'll do this one. I'll just add another one in over here. Because no CDs, if this instead of x is my number of CDs, and this right here is the cost for all of my CDs, if I buy no CDs, my cost is going to be 0, right? If I purchase one CD, maybe it costs me $5. Can I purchase a half a CD? No, so then I would not connect the space between buying 0 CDs and buying 1 CD with a straight line, because the line implies that I'm allowed to exist between those 2 points. And in the context of buying physical objects, you cannot inhabit that in-between space. Or if I'm buying cars, can you buy a half a car? No, you typically want the entire car or none of it, because it doesn't make sense to purchase half a vehicle. Okay? So in those kinds of contexts, we would not include the distance between the points so we don't draw the straight line. I'm going to give you some vocab for this. Things like this we call discrete. Relationship. And a discrete relationship, it's this, or it's this, or it's this. Can't be anything in between. This thing over here, we are allowed to exist anywhere in between the points. We say that this relationship is continuous. An example of something that's continuous would be something like time. Can you have, if you have 1 second or no seconds, can you have a half a second? Can you have a quarter second? Can you have a third of a second? Can you have any fraction of time you want? Yes. So you can inhabit everything between my -1 second here and my 0 second here. So we would draw the line for something like time. So that's an example of something that would be continuous. This over here would be like CDs, buying physical objects, would be an example of something that's discrete. Even some discrete things you can still buy fractions of. Like if you wanted to buy pizza, could you buy fractions of pizza?
Yeah.
But could you buy any fraction of pizza? No. Typically, there are a limited number of pieces. You can't say, yeah, I want 1/16 of that pizza, unless it's already cut into 16 pieces. Typically, a pizza is going to be cut into no more than 10, unless you get crazy holidays at Pizza Hut or whatever, and they make the big squares, and then you get the individual squares. But you can't just go out and get any fraction you want, typically. So we looked at the first three. How about these last three here? Which of those are linear? Which of those are... And talk to me about discrete and continuous as well. Yes, Carolyn.
The fourth and the fifth are not linear because, one is round and the other one is zero. It's not linear.
So neither of these are linear.
Yeah.
Because, sorry, one sec. Because even though we do have some straight line pieces here, it's not a straight line in the same direction the whole time.
What if there's multiple lines?
If you've got multiple lines going on here,
There's a straight line and a straight line. Like, would that ever be a case? I mean, I'm thinking you could, though. No. Not like that. Like, you need, like 3 graphs. Like,
if you had 3 graphs, yeah, you could have that. That's not the implication of what's going on here.
Okay.
But yeah, you could have that, and then each one of those would be individually linear.
Okay. Next one is a discrete relationship.
So yeah, this one was discrete. This one was not linear, but is it continuous?
Mm-hmm.
Yeah, so this is continuous. You'll look at these later on. Things that where the relationship does change as you progress with one variable. And then you got something like this. And Carolyn, you said that this one was linear, and this one's discrete. This one over here was nonlinear and continuous. This one over here was nonlinear, and it was discrete until I drew some lines in there. Okay. So these are just some definitions for you guys. So now when we're starting to look at things, you can say, oh yeah, okay, cool. So that's discrete, that's continuous. There are entire fields of mathematics that deal with, like you can take a course at universities, should you choose to do a math degree, called discrete mathematics. That's all it is. And it deals with the integers, just the integers, which sounds simple, but I assure you it's not. It's less difficult than other math courses you could take, but it's way more complicated than just saying, oh, we're going to count stuff with the integers, and we're going to give you second-year university credit. My sister took that course. I avoided it. So we're going to graph some of these things now. Graphing our linear relationship from a table of values. So we've seen, hands up, have you seen table of values before? And you know how to work with them? Yes, table of values? Okay, some of us, not really. Okay, cool, that's fine. So a table of values gives you a, so this is what it's doing here is it gives a relationship. In this case, it's between x and y. We do not know what the relationship is. We're just told this table represents it. Okay, so what we can do is to figure out what the relationship is, to figure out if the relationship is linear, what we're going to do is we're going to graph it, and we're going to treat these things like an ordered pair, like we did yesterday. So when I've got my x here and my y here, I could just view this as that ordered pair, -6, -4, and I'm going to throw that down on my graph. So I'm going to go over here to this is x, this is y. If it's not stated, x and y are always set up like this. Y is vertical, x is horizontal. So -6, -4 is going to be over here at 1, 2, 3, 4, 5, 6 to the left. 1, 2, 3, 4 down. There's my dot. So now my next one, -3, -1, going to be over here. 1, 2, 3, down here, 1. With those two dots, does it look linear? I mean, could I draw a straight line that connects those two dots together? Yes. But 2 dots is never enough. We need several points to verify linearity. You can make anything look linear if you only look at a certain number of points. So let's do another one. 0 and 2. So my x coordinate is 0, so I am right here, and I'm going to go up 2 to here. Now let's go over to 3, 5. 1, 2, 3, 1, 2, 3, 4, 5. Now we're going to go to 6 and 8. 6, 1, 2, 3, 4, 5, 6, 7, 8. Okay, cool. So now that's the entire relationship graph, or the entire table graphed. Is that thing linear? Can I draw that with a straight line? Is there anything in the context of the question that tells me to not connect those dots? Nope. So then we're allowed. So let's do it. I'm going to grab my ruler. You can use whatever straight edge you may have at your disposal. And we get a relationship that looks like that. Is this thing linear? Yes. And because they have not given us context for the question, we can assume it's linear. sorry, we can assume it's continuous.
Oh.
Carolyn, I saw that hand.
Would you say like would the formula be y equals x plus 1 or 1 plus x with all the numbers? Well,
We'll get there. Neither of the ones that you're warm.
well, it depends how you call it. Like, is a 2 square 1 thing or 2? Like, do you
Assuming
square or do you have 2 squares or 1?
if nothing, well, because of the way we read this, every square would have to be 1.
Okay.
Just because of the way I built my graph that was the assumption I made. So each one of these represents. That's a good question though. Every one of these represents 1, 2.
X plus 2 or 2 plus x.
Yes. We'll get into how that happens in a second, but yes. Okay. So we're going from the table to the graph. Flip the page. Sometimes we don't need the graph though. Sometimes we can just look at the table. You stay on that page. I'm going to flip back here. What is interesting about this table that produced this graph? Looking at these values for x and y, what strikes you as potentially being interesting? Yes, Shyla. X and y are both going up by 3 each time. So to go from here to here, we went up by 3. To go from here to here, we went up by 3. We go from here to here, we went up by 3. From here to here, we went up by 3. On this side, we also went up by 3 each time. Well, that's interesting, and that produced for us a linear relationship. Now I want to jump back to this page. What's happening here in these tables? So in this case, this one goes up by 1 each time. What's going on over here? This one's going up by 2 each time. So what's going on? Is this thing going to be, if I graph this, would this produce a linear graph? It might. Let's verify that for you. Let's just draw us I'm going to do my best to draw one here nice and cleanly for you. I'm going to put my points real close together. 1, 2, 3, 4, 5, 6. My Y ones are going to be weird. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Those are roughly the same separation distance between each one. So my first one was 1 and 5. So 1, 2, 3, 4, 5. Number 2 was 7. 3 was 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 7, 8, 9. 4 and 11. 5 and 13. 6 and 15. Does that look linear? Okay. So what are we looking for then? In the previous table, each one went up by 3. Do they both have to go up by the same amount each time? No. What matters?
But they both each, like y goes up by 1 number each time, not 3. It's not, it doesn't go like, goes up by 2, goes up by 3, goes up by 7, goes up by 5. Like it's, the y is always 2, 2, 2, 2, 4, 3, 3, 3.
Okay. Okay. So what we've got here is we've got the same jump up each time.
Yeah.
But but what if I had done this instead? So what if I tell you, here's the table of values. Here's my x, here's my y. What if I said, oh, I'm going to give you the point 1 and 5, and then I'm going to give you the point 2 and 7, then I'm going to give you the point 4 and 11, then I'm going to give you the point 7 and 17. Is that linear? Where did I pull those points from? Sorry? This table right here is the same as this table here. I just omitted a couple rows and then added a row at the bottom. So this one gave us the same jump up each time. This one's not giving us the same jump up each time. I'm going from 1, so this is a jump of 1, this is a jump of 2, this is a jump of 3, this is a jump of 2, this is a jump of 4, this is a jump of 6. So what do we need? Is saying that the same jump up each time, is that enough? No, it's not. What do we need? Sorry? Yes, it's a ratio. Okay? So we're going to look here, let's look at the ratio here of, and the way I'm going to write it, this is going to be probably different notation than you've ever seen before. That's okay. Will humor me. I'm going to triangle y divided by triangle x. Humor me here. Has anyone ever seen this notation before? Okay, so this is a new mathematical notation for you. This little triangle here is a Greek letter. Maybe you've seen Greek letters before. Did you ever done angle stuff before?
What?
Have you played with angles before in math, middle school? Kind of, sort of? Okay. Have you heard of the angle theta? Is theta ringing any bells? Okay. So then this might be your first Greek letter in math, and that's cool. This little Greek letter here is delta. Teaching you some Greek. That's the Greek letter D, little triangle. And delta represents a change in. So by writing it like this, what I'm looking at is the ratio of my changes in the y over my changes in the x. Okay? So, jumping from 1 to 2 and from 5 to 7, what's my change in y here? Okay. What's my change in x? Okay, so my ratio going from this point to this point is 2 over 1. How about the next guy here, going from 7 to 11 and 2 to 4? What's my ratio in change in y? It's 4 over 2, which is 2 over 1. How about this next guy here? I've got 6, going from 4 to 6, and I'm going I'm going from 11 to 17, which is a jump of 6, and from 4 to 7, which is a jump of 3. So what's my change in y, going from here to here? It's 6 over 3, my change in y, versus over my change in x, which is what? Ratio. That's just going to give me 2 over 1 again. So Presley, you're absolutely right. What we care about not is that the jump is the same each time, or that the individual jumps themselves are the same each time. So first it went up by 3 and 3. It was good, but not enough. Now we're going up by 1s and 2s. We're consistent, but again, that's still not enough. What we care about here is this idea of a ratio. It's a change in my y values over my change in x values. As long as those ratios are the same, our relationship is going to be linear. And that's the definition we're going to put down here. The relation is linear if the ratios, and I'm going to write it as this, and then I'm going to put this on top. This represents a change in y. This guy here represents a change in x. If those ratios are equivalent. Oh, sorry, yes. Actually, better yet, I'll zoom out so we can have it all. So then let's look at these other two tables. Do these two tables represent linear relations or not? This one does? Okay. What's my, going from here to here, what's my ratio? It's going to be -3 over 2. My ratio from here to here is going to be, here to here the ratio is the same, going down 1 but going up, yeah. -3 over 2, -3 over 2. That's cool. So then this one is linear. Then this guy here. What's the ratio going from -3,4 to -2,7? The y is changing, going up by 3. Y is going up by 1. Okay, how about the next guy here? All I got to do is, we can keep going, sure. This one's going to be? This one's all over the place. Is this relationship linear? No. And so we're going to call this thing nonlinear. We don't know what it is, we just know it's nonlinear. And at this point in this chapter, all we care about is whether things are linear or not. Cool? Comments, questions, concerns so far? I know some of the language here is a little different. We cool with the language and how it works? Okay. Wake up. Okay, so in linear relationships, one of the variables is always determined to, or is called the independent variable, and one of them is called the dependent variable. What do you think those words might mean in this context? Rebecca?
One variable doesn't have to change, another one relies solely on
You said one variable.
one variable, so the independent variable is sort of just there, and then the dependent variable is something like
Your voice is trailing off like you're unsure. You're correct. You're absolutely right. So let's give these definitions here. We'll define the dependent variable first, because that's the one that makes sense, most sense to define. The dependent variable depends on changes in the independent variable. Dependent variable. So the dependent variable is not allowed to be whatever it wants. The dependent variable, the value for it is determined by whatever the independent variable is. The independent variable can be whatever you want it to be. The independent variable, how do I want to say that? This one can change however it needs to. I'll say it that way. You can set the value for the independent variable, and the dependent variable you will be given the dependent variable by the independent variable that you've chosen. So, for example, can anyone think of a relationship where one of the things is allowed to change and the other variable depends on what you've changed? How many what, sorry? Which one of those is going to be independent? Which one of those is going to be dependent? So what you're telling me is you can change time by dictating a particular, you said a length. In some contexts, that could work. In some contexts, that could work. Like if you want to go, 10 kilometers, that's going to take a particular amount of time. If you want to go 100 kilometers, it's going to take a particular length of time. Sure. Okay.
I don't know if this makes any sense, but like if there's apples and there's a person, and the person eats, if the person's the dependent variable, and it depends on how many apples there are, or how many apples it'll eat. Like if it eats half the apples that are there, if there's 2 apples, it'll eat 1. If there's no apples, then that means that the dependent variable won't eat any apples.
That is a complicated example.
Or like if there's 4 apples, it'll mean that the dependent variable eats 2 apples.
That is a complicated example.
Okay, what would be?
Rebecca thinks she has a simpler one.
Or if you're putting a pet cat lives.
What do you mean?
Like you move the house, the cat has to come with you.
Oh, sure.
Oh, okay.
Sure.
Yeah.
The place you lived is the place. Yeah, sure. I mean, that's not going to show up in math so often. A more simple mathematical relationship would be something like I mentioned before. Things like cost versus the amount of stuff you want to buy. What's the thing that you change? You change the amount of things you want to buy. What does the store tell you? How much it's going to cost, right? So that is a simple example. So if you want to go back to your apples,
Is the apple one correct?
you choose how many apples you want to buy. The store's going to come back at you and say, okay, it's going to cost you $50. Okay, so things like cost versus, I'll say the number of objects. Typically, I mean, it could go both ways. You could say, I want to spend $100. How much of this can I get? Typically, though, you walk into the store and you say, okay, I want a dozen apples. How much is that going to cost? The number of objects is typically going to be independent. And the cost is going to be dependent. Typically. Could you reverse it? Yes. You could contrive a scenario where that's backwards. Or the example Carolyn gave, where she said, there's a distance here versus time. And the example Carolyn gave said, okay, if I'm going to travel this far, it's going to take me this amount of time. Or if I travel this far, it's going to take me this amount of time. So the way she worded it, the distance is the thing that you're choosing, and the amount of time that that's going to take is going to depend on how far you want to go. So in the context that Carolyn gave, distance is going to be independent. She chose this. And this is going to be dependent. All right. Typically, though, so that's one example. So with the distance versus time example, this is independent, and this time is dependent on how far you want it to go. And that is a more a concrete, like in life, looking into the future. I'm gonna go for a drive. I'm gonna choose how far I'm gonna go, and the amount of time that's gonna take me is gonna be dictated by how far I'm going. In mathematics, though, typically what we do is we go the other way. We analyze what's already happened. If we're analyzing what's already happened, let's say we're looking at the trip that Carolyn took to Vancouver. Carolyn drove to Vancouver. When time is 0, where's Carolyn?
Not moving. Just at home.
At her house, assuming that the house is where she started from.
Yeah.
Okay? At time is 30 minutes, where's Carolyn probably going to be? Yeah, between Langley and Surrey somewhere. So now, in this example, analyzing what someone has already done, which of those variables is independent, which one of them is dependent? Which one am I selecting? I am choosing the time. You're telling me where she is relative to that time. So in this context, it's actually switched. We're picking the time. Time is independent. And what you're doing is this becomes, the distance then becomes dependent. It's dependent on when you look, right? 30 minutes in, assuming Carolyn lives in Abbotsford, she's probably somewhere between 200th Street and 176, assuming traffic is good. If traffic is bad, she might be at Mount Lehman Road, right? So these are all the 3 different examples. This one right here is typically the kind of stuff that we're going to be doing in this class, where we're analyzing something that's already happened. When you're graphing the independent variable always goes on the x-axis. Because in a relationship like this one up here, you're going to see the x variable is always considered the independent variable. Y always depends on changes to x. So for these examples here, we would have things like cost would be up here, and the number of objects would be down here. Or in this example that let's do it on the end one here. The example I gave you with the distance versus time, where I took Carolyn's example and I swapped it, we would say, okay, this one would be distance, this one would be time. But if we look at the example that Carolyn gave, it's like, well, if I'm going this far, time would actually be up here, and distance would be down here, depending on the context of the question. You have to be able to identify the thing you are selecting and then recognizing what is changing as a result of what you've chosen. Cool? Flip the page, one little bit chunk, one more little chunk of language to look at here. Let's put it all together. I have a relation. I tell you, the relation is this. Up till now, the relation that I've given you has been a table of values. Now, no, I'm saying my relationship is actually this. Y is equal to 10 minus 2x. Okay? Here's some more language for you. When we're talking about a relationship like this, we say that because y is dependent on x. I don't know why I wrapped that around. I shouldn't have wrapped that around, but that's okay. We say the language we use for that is that y is a function of x. I'll bring that in here a little bit here. The language we use to represent this is that we say y is a function of x. And there is notation that goes along with this idea of what makes a function. Okay? So we say if y is a function of x, we can write it like this. Now, this is not multiplication. Okay, so that's how we write. This right here is function notation. And it's important to recognize that this is probably the first time you've seen something written like this, where the y and the x here, this is not multiplied together. This is where you'd say, okay, well, let's pick my value now for x, and we're going to see what y is. So what we're being asked to do in the wider question here is we want to fill in this table of values. So that we're given a bunch of variables or values rather, for the variable x, and we want to figure out what my value is for y. So what I'm going to do is I'm going to take my value for x, we're going to substitute into the equation, and we're going to get my value for y. If I put negative 3 in here, we're going to get y equals 10 minus 2 times negative 3. Negative 2 times negative 3 is positive 6. 10 plus 6 is 16. What we've done here, this thing, is actually when we found y when x is negative 3. This is how we'd write that. That's then going to be equal to 10 minus 2 times negative 3. So then we would say that y of negative 3 equals 16. And so then this point here, negative 3 and 16, is the point that would form your ordered pair. How are we feeling about this? Okay. You can think of, when we're talking about functions now in math, this starts to open up a whole bunch of different things. A bunch of the operators, like in the very first chapter, I was telling you, we're going to talk about a bunch of operators, and they're going to do stuff to numbers. I introduced you to a square root, I introduced you to the absolute value. You've already looked at squaring and cubing and those kinds of things. We talked about them as operators, but we can also talk about them as functions. They take in a number and they produce some other number for you. So if, for example, maybe this is a bit of an aside. Do I want to do this? You know what? No, I'll leave it here. We'll talk about more functions later. So let's fill in the chart. I've got negative 3 and 16. What happens if I take negative 2 and I substitute it into my relation here? What do I get? Yeah, it's going to be it's going to be 10 plus what? You sure? If I plug in negative 2 in for x, when y equals 10 minus 2 times negative 2 is? Oh, you went to the negative 1, yes. 10 plus 4 equals 14, so then that y value there is going to be 14. The next one, you're absolutely right, it's going to be 10 plus 2, which is, when x is equal to 0, y is going to be? When x is equal to 1, y is going to be? Is this relationship going to be linear? Probably. When x is equal to 2, y is equal to? When x is equal to 3, y is equal to? We can do this relatively easy in our head. Yeah, or does anyone need me to show you some of these values again?
I mean, it makes sense if we know that it's linear, because then it goes down to 2.
Well, I mean, I can prove that. I can prove any one of these to you. If I just go, so y equals 10 minus 2 times 1. 2 times 1 is 2. This is going to become 10 minus 2, which is 8. Yeah. So that's all this is. So this relationship turned out to be linear. That's cool. One of the things that you can notice that defines whether or not an equation like this or a relation like this is going to be linear is the exponent on x. To determine if an equation is linear, look at the exponent, or they'll say the exponents on the variables. What are the that's really kind of blurry, sorry. What are my exponents on x and y? They're each 1. Linear relationships are defined to be equations where that exponent is 1. Put it above here. Linear relationships will have an exponent of 1. Always.
What if we don't?
Then they're not linear.
Okay.
This is like a definitive is or is not. Exponent 1, yes, linear. Exponent's not 1, is not linear.
Wait, always?
Always.
You just look at.
Always.
Wait, what?
There are no exceptions to that.
Like in,
None.
In the, what did you, no, I'm not understanding. Okay. It makes sense, but it doesn't. I don't know what you're pointing at.
If I give you the relation, if I give you the equation, you can look at it, and if the exponents on the variables is 1,
Then it'll be linear.
sucker's going to be linear.
Oh, okay.
By definition, it will be linear.
So, but if it said like y squared equals.
Then as soon as then all bets are off.
Okay, then it's not linear.
That's not linear.
But it will still be a.
It's a relation. It's a function. We can do some of them are not functions. The relations are their functions. You're going to learn next. You're going to learn next year that there's actually a difference between a relation and a function. I'm using the language here interchangeably because all linear relations are also functions, but not all functions are relations. You'll have next year. Worry about that next year. We'll get there. I promise you. I promise you we'll get there next year. Okay? So, and when I say we, I mean we because it's still part of my course load. So if you're taking Predip 10, you'll be with me. Which could be good or bad, depending on whether you like me as a math teacher. So let's graph this thing. Carolyn brought up an interesting point earlier. She said, are we calling each one of these squares 1? Are we going to be able to do that with this graph here? No. Why? Yeah, because we need 16, and there's not 16 squares up and down. So let's do it. So if I go by 2 here, so I'm going to go 2, 4, 6, 8, 10, 12, 14, 16, 18, which means downwards I'm going to have -2, -4, -6, -8, -10, -12. I do not have to have, this thing is called, does anyone know what this is called? How I've labeled my graph here? There's a name for it, starts with an S.
Once you say it, I'll know.
It's the scale.
Yeah.
Okay, this thing right here is called the scale of your graph. You do not have to use the same scale for the 2 different variables. So just because we went up by 2's here, we do not have to go up by 2's
But it makes it a lot
this
easier.
way. Not necessarily.
Okay. But like for graphing it, if it works.
We're going to graph it without doing the same scale, just to bother you.
Okay.
And to show you that it makes no difference.
It doesn't make a difference, but it's easier if you're like, oh, this one's 2, this one's 2. Or, I don't know. I think it would be easier for me.
Well, then let's make it harder just for fun. Okay? Here we go. So we'll see here the scales for x and y do not have to be the same. You you must be consistent. Like if you say your x's are each going to go up by 1, you better make all of your x's go up by 1. You can't go up by 1, then up by 2, then up by 3. That things get horrible. But the scales for the x and y don't have to be the same. So let's start graphing these things. I've got -3 and 16. That point's going to be right there. Or the point -2 and 14, that's going to be right there. Or -1 and 12 is going to be right there. 0 and 10 is going to be right there. 1 and 8, 2 and 6, 3 and 4. Is that thing linear? You bet it is. It better be, because I told you it was going to be. What would have happened if I'd used the same scale x and y? What would the graph look like compared to this one? I'd have to have dots in the middle of the line, maybe. Perhaps. But would it still make a straight line? Yep, it would be. So looking at some patterns in the graph, how do these patterns relate to the table of values? What's going on? If I'm going from this point here to this point here, what do I have to do? Careful. While that's technically true, yes, I'm going 1 step to the right and 2 steps down, because one of these things is going from 8 to 6. So to go from points, and the graphs, I should make a point of saying here, these things, I'll make a note on the side here. Graphs are read left to right. So when we're looking at graphs, we always want to say, okay, so what's happening as I move from left to right, which has been, you guys have just kind of naturally done that already while we've been talking about these things, but I want to make sure that we always do that. So to go from this point to this point, what am I doing? Well, I'm going over to 1 that way, and I'm going down 2 that way. Is that always true between these points that I've labeled? Going from here to here? That way I'm going over 1, going down 2. Or from this one to this one, over 1, down 2. So I could say, as my x values increase by 1, what are my y values doing? Yeah, they're decreased by 2. Which is going to lead us, do I want to show you this today? Yeah, we'll do it today. Don't flip the page, stay on this page down here at the bottom. This thing right here, it's technically not part of the Math 9 curriculum, but I'm going to introduce it to you now. This thing right here is the introduction to a concept called slope.
Oh, I heard of that.
And slope is, going back to something I've already shown you, slope is the ratio of change in y over the change in x. So then for this graph, what's my slope going to be? Almost. A decrease by 2 needs to be represented as a -2. Cool. So my change in y is -2 as my change in x is +1. That's interesting.
Okay.
Let's go back and look at the relation we started with. Does negative 2 show up anywhere else?
Yeah.
This thing right here, the number being multiplied in front of my x, that is the slope. That number is the ratio of change in y over change in x. And where does that 10 come from? We're going to jump to that one, but I'm going to do it. As with so many times, I'm going to take a step in between, and then we're going to get there. What happens if my x value is 0? This whole term goes away, and y is equal to 10. So this thing is that point right there. And if we go back and look at our graph, this is where our line intersects the y-axis. And so we give this point a name. We say that this thing right here is the y-intercept. This is the point where the line crosses the y-axis. So then this piece right here there is an x-intercept. It's not as useful to us in these ones, but we will get to another style of relation where it is useful. We say that this is the y-intercept. I'm just going to abbreviate it as y-int. And so, this relation right here, y equals 10 minus 2x, we say that this thing is the slope-intercept form for a line. There's a lot going on with one little simple, relatively simple example. Cool? Comments, questions, concerns? How many of you are like, yeah, it makes sense, but I'm uncomfortable?
Yes.
Which is exactly where I told you at the beginning of the semester that I would love to hang you for as much of the semester as humanly possible. Flip the page. I want to give you the rest of class time to play with some of this stuff. Some of this stuff you're not going to see again until grade 10. Some of it you're going to use right now. The questions I want you to do are these ones down here at the bottom. Yeah? You just did.
No, I mean like, no, but apparently last semester IB or pre-diploma, this choose class went slope and they were complaining about it.
You just did. That's
no,
it.
But, no, but she went crazy. I don't know what her.
Well, let's go back here.
No, we don't need to.
No. What's the slope here? No, but okay, so look at this. Okay, so let's talk about what we talked about before. Slope is just a ratio of change in y over change in x. So what's my slope on this line? Let's go back now. You might be, okay, no, forget what the other class may have complained about. Slope is just the change in ratio of y over x. So, what's my slope here? What's my change in y over my change in x? Look what we did here. Going from here to here, we went up by. Going from -4 to -1, we went up. Going from -6 to -3, we went up 3. So it's going to be 3 over 3. So what's the slope? 1. That's it. That is slope. Which then we look at the graph. Okay, so the slope means that for every value, if I go up 1 in x, I should go up how much in y? I should go up 1. So if I go from here to here, 0 to 1, I'm going to go up 1. over 1, up 1, over 1, up 1, over 1, up 1, over 1, up 1, over 1, up 1. That's slope. That's all it is. It doesn't have to be hard. That's all it is. So we can even take this thing a step further. We can say, okay, well, what's the equation then of this line? What is the, because I've given you, we've got a table of values here. Now we've got a line. In the very last example, we started with the equation, then we got the table of values, then we got the graph. Now we started with the table of values, now we got the graph. What's the equation? Well, y is going to equal, I told you before that the number in front of the x is the slope plus the number that came next is going to be my y-intercept. What's the slope? What's the y-intercept? So then my equation is just going to be y equals x plus 2, which, if you remember, was what Carolyn said about 20 minutes ago.
That's right.
It all comes together. Let's do some more. What's this one? What's the equation for this guy right here? Y equals to go from this point to this point, I do what with my y? I go down 2, and I go over 1 in my x. So what's the ratio there of change in x? We're changing y over change in x. It's negative 2 over 1, which I can just write as negative 2. So this one's going to be y equals negative 2x. What's my y-intercept here? Negative 2. Because here's 0, 1, 2. So it's going to be y equals negative 2x minus 2. We can do the same thing here. What's this guy? That's it. Because my y-intercept is 0 and my slope is 1. See, it's not so hard. Slope really isn't that tricky. But we're going to save most of that discussion till Predip 10. And the questions I've assigned to you are right here. 1, 4 to 7, 8, A through D, 9, and 10 ace. Here you go. May the force be with y'all. I'm going to add something here to question number 9. Yeah, I want you to do it here. So take a look at this one. For question number 9, flip over here. I want to add something to your homework. The thing I want to add to your homework is, what is the equation for each? Okay? So you're going to fill in the table of values. The question tells you that the relationship is linear. And then I want you to give me the equation. You can do that using everything that we've talked about here. You can do it. I believe in you. Give it a shot.